RegNeRF, regularizing neural radiance fields for view synthesis from sparse inputs. Let's first review neural radiance fields or NeRF. NeRF optimizes a neural representation for the task of novel view synthesis. More specifically, multi-view images of a scene are given as input. During optimization, rays are cast from the input cameras and points are sampled along those rays. You then feed your sampled points to a neural network which predicts a color and a density. The pixel's final color value is obtained by alpha compositing these evaluations along the ray. A NeRF model is optimized with the reconstruction loss on input pixels, and after optimization you can render the scene from views you have not seen before. While NeRF requires a dense coverage of the scene in the order of 30 to 100 images as input, the goal of this work is to investigate and improve its performance when only a few views, say 3 images, are given as input. Here we show a novel camera trajectory synthesized by NeRF when many images are given as input. We can see that it leads to high quality view synthesis. Let's move this aside and see how NeRF performs with only 3 input images. We can see that the quality of rendered novel views drops significantly. The scene does not seem 3D consistent anymore and floating artifacts start to appear. In contrast, our method leads to realistic renderings despite only using 3 images as input. In a side-by-side comparison, we can see that our method leads to 3D consistent representations and the rendered novel views appear sharper. Let's now have a look at how we achieve this. Consider the following synthetic scene. NeRF only optimizes the reconstruction loss for input views shown in blue here. We have seen that this leads to a degenerate solution for sparse input scenarios. To overcome this limitation, we first define a space of unobserved but relevant camera poses and sample unobserved viewpoints shown in red here. For a sampled unobserved viewpoint, we cast rays through the scene and sample points along the ray. We feed these points along with the viewing directions to our neural network f theta, which predicts a color and a density for each point. Doing this for all points along the ray allows us to do alpha compositing. We do this for the predicted color c hat as well as the predicted depth value d hat. Repeating this for all rays for a given patch, we obtain a predicted RGB color patch as well as a depth patch. We regularize the appearance of the RGB patch by minimizing negative predicted log likelihood provided by a pre-trained flow model phi. The flow model phi is pre-trained on unstructured raw image collections and hence can be reused for any type of scene. We regularize scene geometry by enforcing a depth smoothness prior on the rendered depth patches. We observe that this simple prior removes floating artifacts and leads to more realistic scene geometry for sparse input scenarios. Recall the previously shown comparison to NeRF for 3 input views. We improve the quality of not only predicted novel views, but also the optimized scene geometry illustrated here by the expected depth maps. While the scene geometry optimized by NeRF is degenerate, our method predicts a realistic room layout despite only 3 input images are given. For 6 input views, NeRF improves, but predictions contain floating artifacts leading to cloud-like inconsistencies in the RGB renderings. These are also visible in the optimized scene geometry. Our expected depth maps appear smoother and more realistic. For 9 input views, both methods achieve high-quality view synthesis. For novel viewpoints far away from the input poses like shown here, floating artifacts near the table are still visible for NeRF. This can also be seen in the expected depth maps. Overall, we can summarize that our approach improves our NeRF across all scenarios. We now show a comparison to baselines. PixelNeRF is a conditional model requiring expensive pre-training on many DTU scenes. We observe blurriness in the prediction, in particular around edges and less observed areas. RegNeRF does not require pre-training similar to our method. For 3 input views, the optimized scene geometry is degenerate and novel views are not realistic. For 6 input views, we observe a similar trend for PixelNeRF. While RegNeRF results improve, the optimized scene geometry is still inaccurate and rendered novel views distorted. For 9 input views, predictions become better, but edges still appear blurry. RegNeRF now leads to high-quality view synthesis similar to our method. In a side-by-side comparison, we observed that predictions are less sharp, visible for example in the bricks of the roof. We now compare top-performing methods on the LLFF dataset. LLFF is too small for pre-training and hence serves an example for a test data domain shift for conditional models like PixelNeRF, which is trained on many DTU scenes. PixelNeRF is not able to generalize to this new data domain, leading to degraded results. When additionally fine-tuned, results get better, but they are still blurry. For 3 input views, RegNeRF's predicted scene geometry contains floating artifacts visible at the top or the bottom of shown views. For 6 input views, we observe a similar trend for baseline methods. For 9 input views, PixelNeRF still does not generalize to the new data domain. When additionally fine-tuned, it leads to acceptable view synthesis, but details, for example near the ribs of the T-Rex, are blurry. RegNeRF leads to realistic view synthesis, but a side-by-side comparison reveals that small cloud-like floating artifacts are still visible, for example in the bottom right near the leg of the T-Rex or at the top left near the lamp. We now show some additional results for our method. Thanks for watching.